Hi class, it's me, Mr. Morris, and we're talking today about the relationship between Q and K, or reaction quotient, and the equilibrium constant. So this is kind of an introduction to something we call Le Chatelier's principle, and we'll get into that a little bit more later, but we just want to talk about the relationship between Q and K. To start out, when Q does not equal K, Q is going to change to approach K. It's going to try to become equal to K. Q, so to speak, it wants to be equal to K. So when Q is less than K, that means that there are fewer products and there are more reactants. Remember that Q is equal to the products over the reactants, so it should make sense that if Q is too low, that means that it has fewer products and more reactants than K does, than the equilibrium situation. To reach K, the reaction will shift to the right. In other words, it will shift towards the product side. This shift is going to increase the amount of products and decrease the amount of reactants. So when Q is greater than K, we're going to see just the opposite. We have more products and there are fewer reactants. To reach K, the reaction will shift to the left, and that means it's going to shift to the reactant side. The shift is going to decrease the amount of products, and it's going to increase the amount of reactants. Then, when Q is equal to K, equilibrium is reached. There will be no shift in the amount of reactants and products. So just kind of a recap, when Q is less than K, what that means is that you've got fewer products than you would at equilibrium, more reactants than you would at equilibrium. When Q is greater than K, you have more products than you would at equilibrium and fewer reactants than you would at equilibrium. This is a situation where the reaction is going to shift backwards. The reverse reaction would be favored down here. The forward reaction would be favored at the top. We've got just kind of a diagram here, a graph for you to consider. When Q is too low, it's going to proceed to the right until, or the reaction will proceed to the right until we reach the equilibrium. If Q is greater than K, then we have too many products. It's going to shift in the reverse direction until we reach equilibrium. So again, if Q is 0.55, it would shift to the right because K is 1.45. If it's 2.55, it would shift to the left because K is 1.45, and if it is 1.45, there's no change. It's already at equilibrium. Keep in mind, K is always the same unless you change the temperature. So for a given reaction, K is constant unless you change the temperature. Let's do an example. At 1000 Kelvin, the value of Kp for the reaction is given as 0.338. So we have K. The initial pressures of the reactants are, your pressure of SO3 is 2.00 times 10 to the negative third. That's a reactant, SO3. The pressure of SO2 is 5.00 times 10 to the negative third. That's one of our products. And then PO2 is 3.00 times 10 to the negative 2 atmospheres. That's also a product. We want to calculate the value for QP. So before we get started, we want to be able to set up our equation for QP. QP will be equal to the concentration. I'm sorry, actually we're looking for QP, Kp. So QP is going to be the pressure of SO2 squared, and we square it because of the coefficient of 2, times the pressure of O2 divided by the pressure of SO3 squared. Remember, we're looking for gases, only the states of matter of gas, but all of these are gases in this problem. So here's our QP expression. Again, the pressure of SO2 squared, pressure of oxygen, and then divided by the pressure of SO3 squared. The exponents come from the coefficients. Well, we have the values for all of those pressures, so we just plug them into the expression. 5.00 times 10 to the negative third is the pressure of SO2. 3.00 times 10 to the negative 2 is the pressure for oxygen. And then the pressure for SO3 is 2.00 times 10 to the negative third. I literally plugged it into this equation, so I'm going to square this, multiply by this, divide by this squared. Now make sure that you're following your order of operations or using parentheses in your calculator to make sure that this is done correctly. You should get 0.188, and don't forget that K and Q do not have units. It's just a number, 0.188. Predict the direction of the reaction, the direction in which the reaction will proceed toward equilibrium. Well, we want to compare Q, which we just solved, and K, which is 0.338. K is 0.388, Q is 0.188. Now you have to make sure it's the same Q and K. This has to be, if we're comparing to KP, it has to be QP. It can't be QC. Well, we compare those two numbers. We find that Q is less than K. So since QP is less than KP, we can think of it kind of like a number line. This is just one way of looking at it that might make it easier for you. Since QP is less than KP, if you draw a number line, we would have to go to the right in order to get to KP. It's just a visual way of remembering. It shifts to the right, the reaction shifts to the right or towards products when QP is too low. So the system shifts right, and the reason is because QP is less than KP. When the system shifts right, okay, and this is part C, it says determine how these are going to change, each of those pressures. How will they change as the reaction approaches equilibrium? Well, if it's shifting to the right, that means we're increasing the amount of products and we're decreasing the amount of reactants. So that means I'm going to increase SO2 and O2 because they're products, and I'm going to decrease SO3 because it is a reactant. So decrease the pressure of SO3, it's a reactant. I'm sorry, let me go back. Increase the pressure of SO2 and increase the pressure of O2 because those are the products. Let's do another example. This one is with KC and QC. We've got PbI2 as a solid, Pb2 plus aqueous, and then 2I minus aqueous ions. You notice what we're doing here is dissolving a insoluble or mostly insoluble salt in water, and it's breaking apart into its respective ions. It's ionizing or dissociating. The value of Kc for the reaction above is 1.4 times 10 to the negative 18. A solution's made containing 1.65 grams of PbI2 solids and 0.0040 molar of Pb2 plus ions and 0.0012 molar I minus ions. So we've got the concentration of those two and the number of grams of the solid. So we want to calculate the value for QC. Well, first we need to know how to set up the expression. QC is going to be products over reactants. But don't forget, when we're calculating QC, we're only looking at aqueous solutions and gases. You want to leave this out. We're going to leave this out of our QC expression because it's a solid. If it was a solid or a pure liquid, you leave it out of the QC expression. So our QC expression is actually just Pb2 plus times I minus, and don't forget to square it because of the coefficient. And divided by 1, that's just a placeholder because there's nothing that we're going to include in our expression on the reactant side. So now we can just plug in the concentration of Pb2 plus and the concentration of I minus to our expression here. 0.0040 times 0.0012 squared, and we could divide by 1, but we all know that that would just be the same answer. You end up with 5.8 times 10 to the negative 9th. Again, no units here. Predict the direction in which the reaction will proceed toward equilibrium. We've got to compare QC, which I just found, to KC. Again, they have to be the same Q and K. This needs to be the reaction quotient for concentration if we're comparing it to the equilibrium constant for concentration. So we're comparing those two numbers. Kc is 1.4 times 10 to the negative 18th. Qc is 5.8 times 10 to the negative 9th. You can see pretty quickly that Kc is a much smaller number because that's a large negative exponent. Qc is larger than Kc. So we could think of our number line again. Qc is the bigger number. It's over here on the right. Kc is on the left, so that means that the reaction would have to proceed. It's going to proceed towards Kc. It's going to proceed left, which means we're going to create more reactants. It's the reverse reaction that is favored. The system shifts left because Qc is greater than Kc. And you could also think in terms of whether you have too many reactants or products. Again, in this system, we have too many reactants, not enough. I'm sorry, let me back up. We have too many products, not enough reactants, so the system has to shift backwards in the reactant direction. When the system shifts left, don't forget products decrease, reactants increase. So our products being Pb2 plus and I minus, those are going to decrease, and the reactants being Pbi2 are going to increase. We're going to increase Pbi2 because it's a reactant. Moles of Pbi2 would increase. The moles of Pb2 plus ions are going to decrease, and the moles of I minus ions will also decrease because reactants increase, products decrease.